Hello everyone, welcome back to another video. And for this video update, I want to let you know what it's my plan and what's going to happen after I withdraw from all my classes. Well, essentially, I have decided that I'm not going to cut all ties from college. So what I'm going to do is I'm simply going to do something that's more commonly known as a gap year. So I'm going to wait for a full year, okay, to see what I'm going to do. So of course, in the meantime, I have to work because there's nothing better I can do. So I gotta go work, I gotta raise capital, pay my debt, and then go back and see if I can go back to college with no debt and possibly with some scholarships that I could apply and possibly get, and just pay it off, and maybe pay off the next semester. So we'll see what happens. So stay tuned and watch this video that's coming up. Hello everyone, welcome back to another video of Marin, and this is my very first video in virtual reality, and I'm very excited to show you all the perks and all the good stuff that virtual reality has to offer for you. Well, over here, let's just talk about what VR headset I have. I bought the Oculus Quest 2 VR headset, which is the new one that just came out on October 13. A lot of people say that it's kind of like not worth it because Oculus is like owned by Facebook, so Facebook is going to require to Oculus, the VR headset is going to require you to log in to Facebook with your account. So there's like a whole debate on privacy and like if it's really safe or if Facebook is spying on us. I mean, honestly, I don't really care. I think it's too late to worry about that because we have been, I think we have been recorded or we have been monitored before, and maybe we didn't even realize it. So over here we have something that is called Nanomi. And Nanomi is, well, an application that can help you learn chemistry. So over here you can see that there's this person showing you like molecule, and the molecule is very, very detailed. It's got all the atoms, all the compositions, and everything. So Nanomi is very good to learn about chemistry in three-dimensional space because the really real advantage of virtual reality is that you can actually manipulate stuff in 3D space, in virtual 3D space. And for calculus or matrix, which is also, I think it's just like these two are like the same. They have like a partnership. Matrix and Nanomi have a partnership. Um, and so like this is CalcFlow in VR. This is what it's called. The application is CalcFlow in VR. You can find it on Steam. And you have these three sections or four sections that you can explore. One of them, my favorite, is of course multivariable calculus. You see over here, you have four different, things that you can explore: vector addition, cross products, plane solvers. You can plug in equations and see graphs in virtual 3D space. You can look at double integrals, triple integrals, and over here we have the 3D graphing utilities so that you can observe the equations in a three-dimensional virtual space. And over here we have linear algebra. So this is just, basic linear algebra that you can better understand in virtual 3D space. So, and of course over here we have the extra, which is just, some demonstrations for Mobius strips, and of course chemistry, which is included over here, or physics. They're both, relevant. Electron orbitals, subshells, and density, so that you can observe it in three-dimensional virtual space. Now for today, I want to show you a few things. Let's just explore because I'm new to this. So let's check out the parametrized curves, and let's see how it is.
This is the tool for you. Graph any parameterized function by inputting x, y, and z values along the u and v parameters at the bottom.
Okay, I don't know if you can hear, um, but there was a person talking. I think he was programmed to talk once you enter this program over here. And as you can see, oh, let me just move because my cable is not that long. I gotta get a longer cable. So I almost disconnected my cable from the computer. So over here we have three things, or four things rather, four objects that we can manipulate in three-dimensional space. So over here, we have the entry panel. So this is where you enter the equations, all the values. You enter your restrictions. Over here, we have a restriction. And of course, you manipulate this as you wish. You can add more pages. Okay, you can add more equations. And over here, we have another panel. Let's just put it somewhere over here, I guess. Yeah, let's put it over here. This panel is just like it's kind of like a what you call it? It's just like a guide, or I guess it's a list of different things that you can click on and explore to see how it's going to affect this graph over here, which is the interesting part of this app. So this graph, or this three-dimensional graph, is going to be, this is really the breakthrough of VR, like the fact that you can observe this in three-dimensional virtual space, in such a way that it has some degree of depth, like a very, very, very good degree of depth, because you can observe how much, how deep it is. You can change the scales, so you can make it bigger, you can make it smaller. Okay. And over here, you see this little red dot with a blue arrow, which seems to be a vector. Is going to be a point on this parametrized curve. And of course, it's parametrized because, as you can see, it's not a completely filled surface, right? So like the surface is actually composed of this parameter curve, which is just like a curve that starts over here, and it starts rotating. It starts rotating over here. Okay, I think it's more like counterclockwise rotation downwards. Okay, and then it reaches a maximum radius somewhere at this point. Okay, and then it goes all the way down over here. And of course, the restriction is from 0 to 16 pi. I mean, that's just arbitrary. You could make it anything. And it's just a matter of scales, right? Over here we have the y, this is the x, and the z axis over here. Okay, so that you can see that this is in 3 dimensions. Now, I think this is what is called a click foil knot. Let's click on it and see if that's what it is. Oh no, that's different. That's a different parametrized curve, a click foil knot. We can also click over here on the circle, and we can actually get, the the circle. Oh, it didn't come up. Yeah, something's off over here. Let's see, because I click on the circle, and it should pop up. The entire surface should change, but something's off over here. Let me see. Okay, so let me delete some of these pages. Remember, I'm still exploring this, so I am pretty noobish on how to manage this stuff. Let's see if that works. Okay, but it's just a circle. I don't want to see a sphere. Let's see a sphere outline. Let's see. Oh, okay, there you go. Yeah, that's a sphere outline. And it's a parametric curve. And over here we have the equations. And the parameter, of course, is t. And over here we have what is the value of the parameter, right? So we can manipulate the value of the parameter in such a way, okay, that we see where the point is at a particular value for the parameter t. So let's say that t is equal to 0. Well, if t is equal to 0, we start over here at the top, and then we start moving downwards counterclockwise. Yeah. So you see it's going counterclockwise. And so, and also I want to show you this cool feature that you can actually, I think you have to press A, and then this marker pops up, so you can actually write on it. You could let's say, to demonstrate the direction in which it's going. Now, the only bad thing about it, okay, is that you cannot like change the color. So the only color available so far is black, or at least I don't know how to, change the color. Maybe there's a way that I haven't figured out yet, but I'm gonna keep an eye on that. But yeah, so like, this is just generally to I guess to mark, to outline stuff. Let's say I want to show you that, of course, it's going in this direction, counterclockwise direction, downwards. And also like drawing in 3 dimensions is kind of harder, right? Because you have 3 dimensions to worry about. So you have to worry about depth, you have to worry about the height, the width, the length. But anyways, this is to show you the direction in which the parameter, the vector, is pointing to. Each time when, let's say, I change the parameter, when I increase the parameter, you see that the vector, the blue arrow is the vector at which, okay, where there's direction indicating where the ball is moving, the point, the red point. So if you see that I keep on increasing the value of the parameter t, we get to the final point, which is the bottom. And that's a restriction, okay, which is from 0 to pi, and of course pi is 3.4, 3.1416, and so on. So this is just rounded over here. It says 3.142. I don't know why they would round it. I think it's alright. You don't have to have an exact value. But yeah, that's pretty cool. And of course, if we want to erase, I just go like that. Now let's check out the other stuff. So in order to go back, we just have to click here and we go to the menus to see what else we can see. Let me see. Oh, home, I think. Yeah. Okay. So those are parametric curves. Let's check out the double integral. I haven't really looked at it. Oh, somebody's talking. Can you hear it? Okay, he's saying.
This is double integration of the y variable first. Now start over and drag the red arrow in the other direction. This is double integration of the x variable first. In general, it may not always be
Okay,
possible.
I'm sorry. I'm I'm
It may
um
not always be possible to switch the order
I'm
analytically.
listening to
In this example, we
the tutor that's talking, whoever programmed it, and he said that if you move the red arrow, okay, let's say if you move the red arrow in the direction of the x-axis, so this axis is the x-axis. If you move it in the direction of the x-axis, well, I mean, intuitively you're saying you're integrating with respect to the x-axis, right? With respect to x, the x variable. And if you're moving the red point in the direction of the y-axis, right? This is the y-axis over here, as you can see. It's marked over here, right? This over here is all the y-axis. So if you move in the direction of the y-axis, well, you're integrating with respect to y, okay? And so let's say you move in both directions, So in the y-axis, in the direction of the y-axis, right? And also in the direction of the x-axis. So this is kind of like adding vectors, right? If we add the vectors, then we have a direction that goes like this. So what if we move the ball, the red ball, in this direction, in the direction of the sum of the vectors x and y? So then we have, something that looks like this. And that is essentially double integration. So you're integrating with respect to both variables at the same time. And then we get a volume. It's pretty cool, right? We can even look at it closer and closer, which is, it's just unbelievable. It's beautiful. Look at that. Kind of cool, right? Okay, so that's double integration. You can put, equations over here. You can put whatever you want. I don't know. We could add. Let's say we add. Let's add an x, I guess. Let's see what happens. Oh, we just slant it by z equals x, and that's kind of a cool thing to think about when you add different functions on a graph, it's good to look at how that affects the general outlook of the graph. Now if we move this, if we integrate, we see that the volume is different now. Very cool. Now what if we add, for example, instead of x, let's say we add x squared, right? Would it be like, would it be, oh, let me just delete, I added pluses, two pluses at the same time. So this is the region that we had. And now what if we add, wait, I'm trying to make this bigger. What's going on? Okay. Yeah, so what if we add instead of x, right, which made it slant, okay, with respect to the z-axis, it made it slant like if it were to be z equals x. So what if we add x squared? Would it be slanted in the direction of x squared, z equals x squared? Well, let's find out. We add plus x to the power. Where do I raise this to the power? Let me see. Oh, here, to the power of 2. Oh, okay. So I was right. It was going to slant it in that direction. But of course, the general, the general look of the curve itself is still, cyclic function. So like, it's still defined. This over here, this changes. Okay, in the graph, in these values are defined by cosine of x plus cosine y. That's what defines these changes. Okay, but of course, if we add this parameter x squared, we see that it also has the look of x squared over here. So there is like an z equals x squared for every point, for every plane in the direction of the z-axis, right? Z and y and z and x-axis. So like the planes that are defined by the x-axis perpendicular to the z plane and the y plane are going to have z equals x squared for all values, okay, over here. So that's pretty cool. And of course, we can find the double integral over here. We can observe, we can rather visualize the double integral. Okay, I'm trying to make this bigger, but it's kind of difficult. Let's see. I think I have to select it like that. Yeah, there you go. Okay, now let's move on and no, no. Let's see what else this has to offer for us. Okay, so that's just like one of the few things, the cool few things that this thing has to offer. I'm not going to show everything today. Maybe next time I'll show the rest. But for now, if whoever is a chemistry major or like a chemical engineer or whatever might be interested in looking at this, the electron orbitals, the shells themselves, you can observe them over here. So let's say that we want to look at the 1s shell. Where is it? I want to look at it. Oh, okay. It's right here. It's just like, it's so small. It says it's calculating. Okay, so that's the 1s shell. And of course, it's got a uh, spherical shape. What if we look at the 2s shell? It says it's calculating. Please wait. 40% complete, 52, 66, 80, 90, 100%. So it takes a while for it to calculate, the volume that it seems, or rather, to be more accurate, the probability that you're going to find an electron in the shell. So this is the 2s shell. It's still a spherical shell, as you can see, but it kind of has it kind of has a cavity. So if you see over here, it might have a cavity. Now, what if we look at a 2PZ? What is that? Yeah, I don't remember this. It might be a hybrid or something like that. Oh, look at that. Okay, so yeah, so as you can see, you can um, you can look at different combinations, different configurations of electron orbitals, and yeah, it's I think it's pretty cool to just like look at it. It's something that might not be so accessible for everybody, but it's good to think about this and to just observe to have a better intuition of what this means. Let's go back to the menus or to home. Okay. What else should we look at here? Let's look at the vector addition and the cross
In this
product.
example, we can examine the vector addition of two vectors and the cross product of two vectors. Let's take the red vectors 1, 0, 0,
Okay,
and
so
0, 0.
the tutorial guy is saying that, it's saying the basics, how to add and how to find the cross product of
By
two
adding the
vectors,
respective components,
how to find the
let's take the
sum.
vector 1, 0, 1. This is the vector in the xz plane.
Okay, let's look at the sum of two vectors first. So over here we have two vectors, which are denoted by this, the gray and this two gray vectors, or white vectors. They look more white than gray. And of course, if I use the head to tail method or the parallelogram method, you can see that it makes sense. Okay, it's very intuitive to see the addition of two vectors. Okay, so like if I add this vector with this vector, you're gonna get this vector, the resultant vector. Okay, and you can get the same thing by using the head to tail method. So like if we were to draw like a parallel vector to this, which is identical, but instead of being it here, then we're gonna draw it over here from the head, okay, from the tip to head. So yeah, that's not my best drawing. Let me try again. Yeah, there you go. And then that should be the sum of the vectors. So the red vector is the resultant vector. Um, oops, there you go. So yeah, you can play with it. You can see how, oh, look at that. It's kind of cool, right? How you can manipulate this in virtual reality. So that's the beauty of it. Now let's look at the vector cross product. So for the vector cross product, of course, it's a different kind of operation in mathematics. And what happens is, each of these have to be perpendicular to each other. So that's the principle of the cross product. And over here we can see that, okay, if we manipulate this vector, then the resultant cross product should be the red vector. So by manipulating any of these two white vectors, we can see, okay, the cross product, which is going to be, of course, this red vector perpendicular to both of these vectors. Now, the white vectors don't have to be necessarily perpendicular. As you can see, you still get some cross product. And remember that, the cross product of one vector and its opposite, which is anti-parallel, like in this example, is equal to 0. So as you can see, the magnitude of this vector is 0. It's like, outline over here, it says it. So it's pretty cool. Look at that. What if we make this bigger? Oh, look at that. The cross product is even bigger. It's kind of interesting how the cross product magnifies so much, even though the magnitude of these vectors is not so large, right? The multiplier is just huge. Okay, so next video, I want to take a look at the other stuff. So for today, we just looked at the parametrized curves. Okay, we also looked at the double integral and the vector and addition in cross product. And we also looked at the electron orbital subshell and the densities for whoever is interested in chemistry. For next video, I want to talk about the rest. So I want to cover all of this stuff that's in here. And then later on, I might go to nanometer and just give it a try and see how it works. Even though I was not initially interested to study chemistry, but I think it's good to know. It's good to know how to operate that app. Anyways, thanks for watching. I'm glad that I was able to get this VR headset, and hopefully, I'll make better videos so that it's more intuitive for you to understand calculus in 3D space. Okay, because most students that struggle with Calc 3 or any multivariable calculus course is often because they don't have like an intuitive understanding in the 3 dimensions, right? So it's kind of hard to visualize. But with VR, it's so much easier to visualize everything in 3D space. So I am hoping that I can make better videos to explain and to, better showcase the, the concepts of calculus in multivariable calculus. Okay, so thanks for watching, and I'll see you next time. Thanks for watching, and hopefully next time the video will be just as productive as this one and as helpful. So let me know in the comments what you think about the video, and let me know how I can improve the ways in which I make my videos so that it can better help you understand these concepts. Now for the final point, I want to tell you that Webull is offering 5 free stocks. Okay, it's a limited time promotion. So if you go and sign up with my link that I'm going to put on the description below, you can get up to 5 free stocks, each of them valued up to $1,600, and it's only until the 2nd of November. So you have limited time to sign up if you haven't done already to get 5 free stocks. Thanks for watching.